Today I really want to talk about some things that we've been working on over in the environmental engineering department. And really I want to pose this question for all of you here, but at the same time the answer is yes. We already have advanced treatment happening in town. Two examples of that are we've got a water treatment plant that uses ceramic membranes, and we've got a wastewater treatment plant that uses a membrane bioreactor. But at the same time, I'm always looking for, like, how can we kind of merge what we have excellent students at the university doing with real problems that we have in town. So, and I apologize, this is a little annoying, but this is what has to be done. So, anyway, here's a great picture of Butte. I love this photo because it has a lot of things in it. So in the background you can see the mountains. We live in a wonderful state, Montana, that has ample natural resources. And Butte is here because of natural resource extraction. So you can see that head frame in the foreground. And that's really a symbol of mining. So mining has occurred in the past in town, it's occurring in the present, it will occur in the future. And although it's a great economic benefit to the town, it also has an environmental impact, which is why a lot of people are in this class. And it's also a reason that I thought that Butte would be a really interesting place to teach and study environmental engineering. So just if we take a step back and look at town from space, you can see this huge mining complex around the Berkeley pit. You can see the Berkeley pit. You can see the tailings pond up above it, and you can see the active mine over here. And so really, I was interested in, what are we doing with this mine waste? How can we treat it? How can we turn it into something that's actually useful? So you might be looking at the Berkeley pit or other bodies of water that are similar to that and think, oh, why can't we just get rid of this stuff, right? It doesn't look that pretty. It seems like there are always geese landing in the Berkeley pit. Sometimes it works out very badly for the birds. Why can't we just get rid of it? So the problem is that this water is actually really difficult to do anything with because it has very poor quality. So it has a very high pH. So pH is a measure of the acidity of water. So it's like lemon juice almost. That's how acidic it is. It has, and it has a whole lot of metals in it. So it has hundreds of milligrams per liter of metals and grams per liter of sulfate. So this is pretty nasty stuff. And it's not so easy to just say, oh, well, let's just clean it all up. So today, I've separated this talk into 3 different parts. So first, I'll go over just kind of what is acid rock drainage. I'm sure almost everybody in here knows the answer to that question, but I'll go over it anyway. And then I'll give you just a little background on kind of advanced methods of water treatment, specifically the use of membranes. And then I'll talk about one project, membrane distillation of acid rock drainage. That was a project that a graduate student of mine last year worked on. And then that will be the bulk of the talk. And then I'll spend just a brief period of time talking about 2 other projects. One is looking at metals recovery from acid rock drainage and other similar types of waste. And then the other one is looking at enhancing the evaporation in evaporation ponds, which is a project that a senior design group worked on last year in environmental engineering. And this year we have a senior design group who's continuing that work. And that's a collaborative group between environmental engineering and metallurgy. So, acid rock drainage. So acid rock drainage is a natural process. And it just happens when you have sulfidic minerals that are coming into contact with oxygen and water. So basically, when this reaction occurs, you get iron hydroxides, which are basically like a red precipitate that you might see in creeks that are affected by acid rock drainage, or if you go out and look at the pit, there's quite a bit there. It also produces sulfate, and it produces protons or hydrogen ions. And this is what makes it acidic. And although it is a natural process, this process can be exacerbated by earth-moving activities, such as what you would see in mining, because you're basically exposing those minerals to water and oxygen. So I did mention that this water was really nasty, and it is somewhat difficult to treat, but there are ways of treating it, and we actually treat it in a few locations around town. And the primary way to treat it is through the addition of lime. There are other ways, but this is one way. And basically what you do, you add lime. Lime is a base. It interacts with both the metals in the mined waste, but it also raises the pH. And when it raises the pH, those metals which were soluble at the low pH condition are no longer soluble at this higher pH. So they precipitate to the bottom. And what you end up getting after you do this is you get a sludge and you get some sort of effluent, right? So your sludge has all of those precipitated metals in it. You have to come up with something to do with that. And then the effluent is much cleaner water that you can do something with. So in the example of the Horseshoe Bend treatment plant, which is right here, that's right by the pit, they put the sludge back into the pit, and then they use the water. MR uses the water. And in the case of the Butte treatment lagoons, down close to the visitor center, they dry out the sludge and then dispose of it, and then they release the effluent, the water, into Silverboat Creek. So this is a very good process, and it works. But I was thinking of how can we increase the flow rates of these processes. So especially with like the Butte treatment lagoons, you've got like a 7-day retention time. So it takes 7 days for all of the sludge to settle. And can we do this process without adding anything? So how can we get rid of that lime addition step? Maybe we could come up with a process that doesn't require any chemical addition. So that brings me to membrane filtration. So I think that it's awesome in town that we already have a couple membrane plants. This is really unique, especially for a pretty small town. But in membrane filtration, basically you've got your feed, and that's your dirty water, and it comes into contact with this membrane. So these membranes, most of the time they're made out of polymer or plastic, and they have holes in them. So some things can go through the holes. If something goes through the holes, that'll end up in your permeate. That's your clean water. If something doesn't go through the holes, maybe it's too big to go through the holes, that stays in your water, which we then call a retentate or a concentrate. And so whether or not something goes through the holes depends on the size of the holes, right? And the size of whatever you're looking at. So for example, in microfiltration, your holes are going to be on the order of about half a micron. So just for size reference, a bacteria is about a micron in size. And so in this case, so in microfiltration membranes, you could remove bacteria and protozoa like Giardia or Cryptosporidium. So actually, if you happen to have a camp filter with a pump, or there are some straws that they sell as camp filters, a lot of these are actually microfiltration membranes. So you might have one at home and not really have thought about it. If you make those holes even smaller, that turns it into an ultrafiltration membrane. So these membranes they remove bacteria and protozoa just like the microfiltration membranes, but they also remove viruses. So think of like a rotavirus or something that causes a cold or gastrointestinal illness. You can remove those as well. So viruses are on the order of tens of microns. And then finally, if you make the holes really small, and really you're starting to get in nanofiltration and reverse osmosis, you're starting to get more into diffusion rather than holes, diffusion through a thin polymer layer. Nanofiltration membranes will remove things that cause color. So those are like larger organic molecules cause color. And they also remove hardness in metals, so your multivalent ions. And then finally, reverse osmosis is what a lot of people have heard of. That removes salts. So that will remove monovalent salts like sodium and chloride. That you'll see, like if you wanted to drink seawater. You can't drink seawater because of the sodium and chloride in it. So you can use reverse osmosis to clean it up. And also, I realize this is a pretty technical talk, so if I say something that you don't understand, just yell at me, and I'll explain it. So, looking a little more closely at reverse osmosis, because a lot of people, when I talk to them about membrane distillation, they're like, oh, how does that compare to reverse osmosis? They're similar in that they both give a very pure water. But at the same time, they're also completely different. So in reverse osmosis, you have the semi-permeable membrane. That's your reverse osmosis membrane. And you have two streams. You have your feed, which is very salty, like seawater, and then you have your permeate, which is your clean water. And those are separated by this membrane. And you might remember from biology, if you have a salty solution separated by a membrane through which only water can pass and not salts, and then you have clean water on the other side, what happens? So the water travels exactly from the clean water and it goes over to the salty water side. That's exactly what happens when you pour salt on a slug, right? That's osmosis. So that difference in osmotic pressure here is called delta pi. But that's not what you want in a water treatment system. You don't want to produce less salty water, you want to produce more clean water. So we have to overcome that osmotic pressure by applying a greater hydraulic pressure. So you basically just force water to go the direction you want it to go through the membrane. And the rate at which you can produce water is the flux, or JW, and that's going to be proportional to the difference between your pressure difference and your osmotic pressure difference. So basically what that means is if you have saltier water, you need to use more pressure. So these membranes are really cool. And I did a lot of work with them during my PhD. But basically, the vast majority of the membrane thickness is just structural. It's because you have to apply that hydraulic pressure. And all of the selection happens at this very, very thin layer that's on the very top. So that's the polyamide selective layer. And that's important because whenever you're considering using reverse osmosis for a process, that polyamide is pretty fragile. And it can be damaged quite easily. So one thing that damages it is chlorine, which we use a lot in water treatment. So despite the fact that you have to use a high pressure, membranes are easily damaged by chlorine, so they're pretty hard to clean. Reverse osmosis is very widespread. And here's just one picture of a plant in Israel that treats 80 million gallons of seawater a day, which is 15% of Israel's water supply. So this is not like a fringe water treatment process, it's very mainstream. But today I'm going to talk about membrane distillation. And so this is mostly the work of a graduate student in environmental engineering, Eric Hull, and it was funded by NSF, the Montana EPSCoR office. So now I said that the driving force for reverse osmosis is pressure. So you force water through the membrane. Membrane distillation is different in that the driving force for membrane distillation is temperature. So you basically have, here's your membrane. You have hot water on one side and you have cold water on the other. And these membranes are also very different than what you would see in reverse osmosis. So reverse osmosis was all about that really thin selective layer. Membrane distillation has a hydrophobic porous structure that acts as the membrane. So hydrophobic means that water, it doesn't like water, water doesn't like it. So unless you apply a great pressure to this membrane, these pores will remain filled with water vapor. So you've got water vapor that's separating your hot and your cold streams. And so what that means is that water on the hot side is going to be evaporating here and condensing here. And because you have this evaporation and then condensation, it will remove a lot of things. It will remove basically anything that isn't going to evaporate. So things like salts, they stay behind. And because it's distillation, you have a very pure product water. So just to kind of delineate the differences, here we have reverse osmosis, which is pressure driven. It has this dense selective layer on the top of the membrane. The rest of this membrane is structural for the separation. It matters some, but not a whole lot. Membrane distillation is thermally driven. It has vapor-filled micropores in the membrane. And also, while reverse osmosis needs a high-quality energy to generate that pressure, membrane distillation only needs a temperature difference, so you can use much lower quality energy. So things like solar energy or, in our case, geothermal energy are good ways to run a membrane distillation system. And that's another reason why I was like, oh, maybe this is something that we could use in Butte, because we have ample geothermal energy. So this is a schematic of our lab system. It looks kind of complicated, but the important parts, here's our feed reservoir. So in these experiments, we put a synthetic acid rock drainage in that feed reservoir. And then it just loops around. This is a pump. And then it goes into the membrane chamber. And then we measure its flow rate, goes into a heater, and then it goes back to the reservoir. And the distillate is the same. So the distillate goes out, goes through a pump, goes into our membrane chamber. We measure the flow rate, goes to a chiller, and then it goes back to the reservoir. And basically, as water vapor is traveling from the hot side to the cold side, that's increasing the volume of the cold side. And so we measure that increase in volume. Here we've used a drop counter, or you could just measure the mass as it overflows. So this is our synthetic acid rock drainage. And just for comparison, I compared it to the Berkeley pit water. This isn't everything that's in the Berkeley pit. The Berkeley pit has a lot more stuff in it. But this is just some numbers to compare to what we used as a synthetic. And so you can see there that we have a pretty low pH, a reasonably high conductivity, almost a gram per liter of iron, and then some zinc, copper, and aluminum in there as well. And of course, quite a bit of sulfate. So this is the process that we proposed. So and we wanted to keep it as simple as possible. So we take a synthetic acid rock drainage, we stick it in our membrane distillation system. 80% of what we put in our system, we get out as clean water, and then 20% is concentrated waste. So we did this, and we saw some pretty interesting results. So first of all, we're actually able to treat 80% of the water, which was really awesome, I think. So the membrane didn't fail before that happened. But what we did see is over time, so flux is basically the water production rate. We saw that decreased with time. And this is the water quality of the distilled water with time, which you would want to be pretty constant, but we saw that concentrations, so here's conductivity, here's sulfate, so those are increasing with time. So that's basically telling us that something's wrong with our process. The quality of the water that we produce is getting worse and worse with time. And additionally, we're not producing as much with time. So this isn't great. And then we took the we can take our membrane cell apart, we can look at the membrane, and what you can see is that while clean membranes are basically just gray, they're just gray polymer sheets, after we use them, we saw all of this deposited material. So we call this scale. And it's red, it's iron-based. And because this material is depositing on our membrane, that's affecting the efficiency of our process. So that's what's making our water production slow with time, and that's what is decreasing the quality of the water we produce with time. Oh, and this one isn't going to work at all. But anyway, so we also just looked at the system and we saw some iron precipitates forming just in our system. So not only on the membrane itself, but also just in the reservoirs upon heating. And so you can see, maybe, you can kind of see little flakes around there. And those are basically iron precipitates that form when you heat up water with high concentrations of iron. And so this got us thinking, why don't we use this thermal, this thermal phenomenon where iron is falling out at higher temperatures as a pretreatment? So basically, we're getting an iron precipitation without the addition of any chemicals, so we don't have to add lime to make this happen. And we're already heating the water anyway in order to carry out the membrane distillation process. So, and you can't see the other ones, but so basically this is with this iron pretreatment, we've got this is a higher pH, and we have much lower conductivities, much lower iron. Iron was closer to 1 gram per liter when we started out, so it's much lower. And we have much lower sulfate as well, just after doing this thermal pretreatment. So here's a schematic of our new process. So we have synthetic ARD, we heat it, we form this precipitate, then we send it to the membrane distillation system, we get clean water and a concentrated waste or sludge. And basically what we see is that this improves our system performance. So you don't see quite as much of a decrease in the water production rate with time. And we don't see that increase in any of our water quality indicators in the distillate. So remember, in the last graph, this was increasing with time. And here it's actually decreasing. So this thermal pretreatment is really good for improving water quality. And also, when we look at the membranes themselves, they look much better. So this is the membrane with just the synthetic acid rock drainage when we just threw it into our system. We got all of that scale formation, all of these iron precipitates that formed on the surface. And when we pretreat it, we see much less. Also, we didn't just see these iron precipitates on the feed side of the membrane, so the side of the membrane that came into contact with the really dirty water, but we also saw them on the other side of the membrane, which was contacting only clean water. So you can see that here. And so basically that means that these minerals they're colonizing the surface of the dirty side, going through those micropores, and then they're coming out on the clean side. But we don't see any of that when we do the pretreatment. And I don't like to just look at things and say, oh, that's great. I like to measure stuff. So one way to measure this is with contact angle. And basically, this is when you put a drop of water on the surface of your material, and you see how that drop of water spreads out. So if that water balls up, there's a high contact angle. That means the material is hydrophobic. If the water spreads out, that means that the water likes the material. That it has a low contact angle. That means the surface is hydrophilic. So when we don't pretreat, we see a more hydrophilic surface on both sides. Whereas when we pretreat, we don't see any significant difference between the surface, either side of the surfaces of the membrane. So we're treating our membranes much better when we do this pretreatment. And likewise, we look at we can probe the inner pores of the membrane by looking at how much force we have to apply to water to push it through the membrane. So here you can basically see that so this is the force required to push water through the membrane. As we distill water, that force decreases with time. That means it's much easier to push water through the membrane. Our pretreatment actually doesn't change that. So these blue squares are the pretreated. So we've improved some of the effects of the membrane by doing the pretreatment, but we definitely haven't eliminated all of the effects of scale formation on the membrane by doing the pretreatment. Okay, and finally, if we have any chemists in the room, we characterize the scale. So the scale happens to be goethite, which is an iron oxyhydroxide. So to sum up that part, so we can use this membrane distillation to treat acid rock drainage. We tried this with a synthetic acid rock drainage that we just made in the lab. Some scale forms, and it's a hydrated ferric oxide. And this scale kind of impacts the process, makes that process not as efficient, but we can do this thermal pretreatment to negate many of the effects of scale formation and improve distillate water quality. So that's kind of the main thing I wanted to talk about today. But I wanted to just kind of give you a flavor of some other things that we've been working on. And this is specifically 2 projects. So this metals recovery project is a pretty big collaboration that we came in kind of towards the end, but it's headed by Jerry Downey at Montana Tech and Ed Rosenberg at UM. And a graduate student, Christina Eggensberger, has worked on this. And then this enhanced evaporation idea, which is something that a senior design team worked on last year, and a senior design team is going to continue the work on this year. So in this process, basically the point of this process is to take a waste, acid, mine drainage, or something similar, and selectively remove the copper. So the Berkeley pit, for example, has tons of copper in it, in the water, but it's very difficult to get at that copper and turn it into something that's useful. So in this process, you take that waste and you have particles that selectively absorb copper. So that's in this step. So we selectively absorb copper to these particles. This is a whole project in and of itself, but I'm not going to really get into it. But the particles have a magnetic core that enables them to stay within this flow reactor. But you can take the nanoparticles out periodically and wash all the copper off, and then put those nanoparticles back in the reactor. And so then you can take this washed off copper, and their original idea was to put it into an electrowinning process, where you can basically take out just solid, you can plate out solid copper from your solution. But the problem that they were running into is that the concentrations that they were getting out of their wash step were not high enough to put into the electrowinning step. And so I said, oh, okay, well, this is an opportunity for membrane distillation to concentrate those metals and bridge these two steps. And so we had a student do that, and she showed that it actually works really well. Because we didn't have the solubility problems with copper sulfate that we had with iron sulfate or iron hydroxide in our other system. And so here, this is water production over time. You can see that it's very constant. It doesn't dip off like the last set of data that I showed you with that. Whereas the distillate water quality over time was pretty good. We had some increase in copper concentrations. So we're still seeing some copper going through the membrane, but we were able to concentrate the water. So here's the starting concentration, and then we concentrated the water 3 or 4 times, or 3.5 times after this process. So this is a nice way to bridge kind of those 2 gaps, or that gap. And then finally, enhanced evaporation. So I'm just running through these last two. But basically, the idea of this project was, is there a way to increase evaporation rate on evaporation ponds? So the Berkeley pit isn't really an evaporation pond, but you could imagine a scenario where increasing the evaporation rate would lessen to a small degree the amount of water you had to treat or the time it would take to reach the critical level. But this really isn't the best solution necessarily for the Berkeley pit. But kind of the idea behind this is that there are certain types of nanoparticles that absorb light. And kind of depending on the type of nanoparticles, they can either absorb specific wavelengths, or in the case of like carbon-based nanomaterials, they absorb a broad spectrum of light. So they absorb that light. To some extent, they scatter that light, so that light bounces off of them. And when you have a really high concentration of particles that are absorbing and scattering light, they heat up the water in their immediate environment. And so you can see here is a picture of just light scattering. So you've got, this is a picture of a laser going through a nanoparticle solution, and you can see that light going through. If you increase there's higher concentrations of nanoparticles, you see that light concentrating at the surface. If you increase that concentration even further, you really concentrate the light at the surface. And basically what happens is that you have localized heating at that surface, and you can produce steam with not so high of a light concentration. So in the interest of time, I'm going to skip a few slides. So this is kind of getting to what that senior design group was doing last year. So basically, they were basing their work off of a material that was described by this group, it was a group at MIT. And basically, they have a hydrophobic absorbing, or hydrophilic absorbing layer. So that's a layer that grabs the sun energy and absorbs it, and then it heats up right at the very surface. And because it's hydrophilic, it sucks water up, right? So it's got some pores in it that suck water up. And below that, there's like an insulating hydrophilic layer. So that's keeping the heat at that surface, right? So that heat's not being lost to the water below it. Because if you were losing a lot of heat to water below it, you wouldn't actually be heating anything up. And so basically what happens is that this structure is porous. It pulls water up from below. That water is heated when you shine light on it. And this can actually produce steam or water vapor. And so they were working on seeing whether or not you could apply this to a tailings pond to enhance evaporation. And they actually saw that you could. So they looked at a large number of materials. I only put 2 here, but I think they looked at like 6. But basically, so this is the evaporation rate, and we normalized it to the amount of energy that was shining on each of the samples. And so this is your control. That's just no material at all on the surface. This is a carbon foam, and you can see that increases the evaporation a little bit. And then they put some powdered activated carbon on top of that carbon foam, and they saw a further increase in evaporation rate. So I thought that was pretty interesting, and it could be really nice for evaporation pond type situations. And then the senior design group this year is going to work on kind of using recycled materials. I think at least, no, I see 2 of them, 3 of them. Yeah, they're all here. So I'm going to just put words in your mouth for what you're going to do this semester. But they're going to be looking at different types of recycled materials that you could use, looking at different coatings that you could put on those recycled materials, and then also considering how birds would interact with this type of material if it was floating on a surface. So with that, here's a quick summary. So we showed that membrane distillation is a good way to treat synthetic acid rock drainage. We did this thermal pretreatment, which greatly improves the membrane distillation process. We can use membrane distillation with other technologies for purifying copper or other types of metals from mixed wastes. And then we might be able to use carbon materials to enhance evaporation rates. So with that, I would like to thank you for your patience and welcome any questions.